I wrote to the train station, remember my train was late last week.
Yeah.
So they gave me €6. Well, that's better than no euros. That'll buy me lunch one day, so that's okay. Alright. Shall we continue?
Yeah.
I don't know if we'll get all of this covered. We'll try. Lots of pictures in it. Okay, conservation of energy. You got that? Yeah. Okay. Right. What is energy? That is, if something has energy or is energy, then what do we mean? So we kind of know this word already. Like, energy is a word we use. I'm low on energy. My phone has a lot of energy. You know, what do we mean when we say energy, though? Even though we kind of know it, what do we mean?
The ability to do work.
Yeah, it's the ability to do work. So the definition in physics is something has energy or is energy if it has the ability to do work. The work we mentioned in the previous lesson. Okay? So, for example, I have energy because, I just about have energy, because I could do work. Okay? What else has energy? Well, we'll look at that in a moment. So it's a simple little definition, but it's an important definition in physics, and it's something you would need to know for the exam, I'd say. It's like a one-mark question. You know, what is energy? The definition of energy. It's the ability to do work. Straightforward enough. And you know what work is. We did that just a moment ago. Okay, we continue. Yep. Now, it's also measured in joules. No work, no energy. No energy, no work. Simple as that. If you want something to do work, it needs energy. If some work is done, it means there was some energy. You don't need to write that little part down. Now, technically, if you think about this, the work done is always less than or equal to the energy. Okay, so when I do some work, I have energy in joules, and I'm doing the work, and the work is in joules. This work done here will be less than the energy I have, right? Because I can continue to do work. Yeah. It's only equal if I use all my energy pushing this, and then I have none left and die. Okay. So usually the work done is less than or equal to the energy. However, in physics, so the example I have is 1 megajoule of energy means I could do up to 1 megajoule of work. I couldn't do more. Often in the physics problems we look at, we find that the work done equals the energy. So like usually, you know, if there's some question about, I don't know, something is moved, then often we say the work and the energy is the same. You know, if there's some like thing that pushes this, we say, oh, this energy equals the work done. Even though really all we need is this to have more energy than the work done. So I'll try to be careful, but often you'll hear me switching the words work and energy. You know, I'll say work when really maybe I mean energy, or I'll say energy when really I mean work. Because for the physics problems, they're often the same thing. Just like distance and displacement. You know, sometimes I'll say distance when I really mean displacement, but often it's the same thing. So just be careful with that. Alright, just be careful with that. Okay, there are many types of energy. That is, there are many types of things that can do work. Let's look at them. So picture time. Right, the first type is electrical energy. The only thing I need you to write down is just the name of each type. So you can just write in your book, look, just write types of energy. Right, so the first one is electrical. Oh, getting closer to pizza time. It's exciting. So I have 4 classes this morning. Then I have to teach the science students again after lunch. They tire me. They're so tiring, those science students. There's too many of them. Right, electrical energy. obviously an important form of energy, especially for modern life. You know, so many things are getting their energy via electricity. It's so common. Right, magnetic energy. Now this is interesting because you don't really think about it, but magnets do have energy because it can do work. In this picture here, what work is the magnet doing?
Gravitational.
Yeah, not gravitational, no. Well, I mean, okay, just keep it simple. It's lifting. Like the example with the mother lifting the child. This is the same thing. You know, so magnetic energy is a type of energy. I never think about magnets having an energy. I always think of them as being something different, but they do have an energy because they can do work, because they can apply a force and move something.
Wouldn't
You know?
every particle with mass in the universe have energy in it?
Yeah,
The ability to
yeah, correct.
So when you said you die, you'd have no energy, that's not true.
I'd have to be more precise. I'd have no
You'd have to
chemical
die,
energy.
You'd have to be in a vacuum. And you'd have to
No, I'd have to cease to exist to
Yeah.
completely have no energy.
Singular
Yeah,
particle in,
Yeah,
in
yeah.
its own universe. To
I'd have no biological energy.
Yeah.
But you're right. Ultimately, everything does have some kind of energy, some form of energy in it, and that's actually something we'll get back to in a moment. Magnetic energy, fine. The most delicious form of energy, I think we can agree, chemical energy. By the way, I discovered a lot of teachers have tasted electricity before. I don't know if this is something you've ever done. It is not as nice as chemical energy, which is more delicious. What I've discovered, what a lot of teachers used to do as a kid, now, no, I've never done this, okay, but I was surprised by how many teachers have done this. They've taken, the 9-volt battery.
I've done that.
You've done this, okay. The 9-volt battery, the square battery, yeah, and just go straight on the
It
tongue.
tastes very metallic.
Yes. Yeah. So Zach has done this.
Yeah.
Has anyone else? No.
With it
I don't remember, but I feel like I might
It's
have.
when the two terminals are on the same side, so
Yeah.
you can just bridge
Yeah.
it with your tongue.
Yeah, straight on the tongue.
So it,
But ask Zach now. He's done it recently.
it tastes very, like if you know what blood it tastes like.
Oh,
It smells like that very iron,
I think,
metallic smell.
I
Yeah.
Or
remember.
when you're grinding something like with an angle grinder, steel.
Has this kind of smell to it.
It tastes like that.
Metallic.
Yeah.
Metallic. Yeah. Okay.
So
Right.
Get poisoned?
Well, I wouldn't recommend doing it, but it's probably okay. Right. Chemical energy. That's an important type, and you know about this type in chemistry as well. With the bonds and things like this. Radiant energy, just to be precise here, radiant, I mean in like from the sun, like a solar energy. But it's not just light, technically. It's the whole energy that comes out of the sun. It's just we only see the light. But, there's other energy too, like UV. UV? Do you know UV? Yeah. Yeah. Yeah, UV light, yeah. Yeah, you don't see this light, but it's a form of energy. All of this type of energy is called radiant energy, coming from the sun. Do you know what? You look a bit confused.
No, I was thinking, because my presentation topic is about electricity, and I was talking about
All right.
nuclear reaction.
Yes, that's a type of energy too, yeah.
Yeah, but it's the energy is come from some neutron. And
Correct, yeah.
That's the stars,
Yeah.
It's hydrogen turning into.
Well, this radiant energy was a previous energy beforehand, which we'll get to later. It was nuclear energy, yeah, and then it becomes radiant energy as it leaves.
Oh,
You know.
okay.
Yeah. The radiant energy is how it gets from the sun to the earth in this form.
Yeah.
Yeah. Okay. Next, nuclear energy.
I heard someone say this on the radio. He's obviously trolling, but he's like, so nuclear energy is this new and clear type of energy. That's why it's called nuclear.
Oh dear.
Wow.
Much better than nuclear energy.
Yeah.
The old ocular unclear energy. Yeah. Nuclear energy is a very important form of energy. In my opinion, it's really necessary for future countries to have nuclear energy. Because the fossil fuels, it's limited in supply, and it's not going to be around forever, and it's causing damage. And I think nuclear energy, the new nuclear power plants are quite safe. It's the old ones that are the problem. Also, the other problem is in Japan, it's not that the nuclear power plants were old, but just that the tsunami, broke it.
Yeah.
So some countries are good candidates for nuclear. So to be honest, most European countries are safe for nuclear because there's no natural weather disaster like a tsunami to worry about. America, there's some parts where it would be hit by hurricanes and things. You'd be concerned. Europe should probably have more nuclear. I don't know whose home countries have nuclear energy.
So in China, our nuclear plant is always near the oceans.
That's necessary too, and we'll see why that's necessary too. So China has nuclear.
Yeah.
South Africa.
Yeah, we have, I think, one nuclear power plant, but we signed a deal with the Russians, of course, to, in the future, build more.
Oh, okay.
Yeah.
With Russian construction.
Yeah.
Yeah.
My brother.
They don't have a great track record,
I know this, so I don't know.
Yeah. Maybe they offered to do it cheap.
And it was quite a shady deal.
Of course, these things always are. These things always are.
Money being.
Yeah. These things always are. Does Vietnam have nuclear power? No nuclear. Your home country is.
Malaysia.
Do they have nuclear?
No.
No. And China as well. Yeah, nuclear.
I think our nuclear station is more for research.
It's a research plant. Yeah.
It's a
Okay.
research plant instead of providing energy for.
Yeah.
So nuclear engineering is a chemical field or the physics field?
Oh, I would say it's more physics, but I mean it's going to have both in it. But it's really physics, nuclear engineering. But I mean, there's a like nuclear cleanup would be chemical, I would think. Like how do you clean up the waste? The process. You have these big, huge tanks, and I'm not sure what it is, but cleaning up nuclear waste is a very difficult thing to do. A long process, I think.
Yeah, it takes centuries.
Yeah. Okay, nuclear. Next, this one. You know this one from chemistry, right? Ionization energy. Yeah, have you done ionization?
We haven't learned about the energy that it gives off.
Okay, but you're familiar with the word ionization energy. Okay. Elastic energy is actually an important type of energy in mechanics. Elastic energy. Now the next one is gravitational, because if you think about it, the gravity can do work because it can also apply a force and pull something down. Gravitational energy
That's why I said every particle with mass in the universe
has gravitational. It also has magnetic, I think,
Yeah.
and if it's charged as well, Gravitational energy per particle is practically zero.
But it's not zero.
It's not clear, it might be, because you could be, Zach, you could be at a scale that's so small that the only value it could be is zero. Yeah. It's a very weak force, gravity. Okay, next obvious one is heat energy. Also, Zach, heat energy is something that's always present everywhere in the universe. So you might think, oh, what about if you're very, very, very far away from a star or a sun?
Yeah.
There's no heat. But there's still leftover heat from the Big Bang.
Yeah.
So no matter where you are in the universe, there's always at least a little bit of heat energy as well. About 2 or 3 Celsius above absolute zero. So it's still cold, but still a little bit of heat. Mechanical energy, like in old sort of a clockwork system.
Like the pendulum.
Yeah, just a bit more complicated perhaps, like in my picture here. You know, you wind it up.
Yeah.
It has a mechanical energy. Yeah. Now, wave energy. In my opinion as well, this is another form of energy that is important for the future, especially in Ireland. Okay, the coast of Ireland on the west gets a lot of wave energy. Okay, if you look at all the coasts in the world, I think Ireland is possibly number 2 for most wave energy it receives from the ocean. Now it's obvious why, because we're here and we have this entire Atlantic Ocean hitting into us. Okay, so there's a lot of wave energy off the west coast. I don't know if you've ever seen how they take the wave energy. There's these little, they look like little buoys. They float on the water, and as they bob up and down, they're tied to the floor with a string, so they're bobbing up and down, and this takes the energy. It charges like a little generator as it bobs up and down, and they just send the energy down the wire into the town. You know, so the wave energy, and also, which I didn't mention, which is related, the wind energy, again on the west coast, potential for a lot of energy. So in Ireland, I think we're building a connection between Ireland and France via the UK. So the energy that is produced here can be sent to France via this connection, you know. So I don't know, is anybody, no, I don't think anybody's doing green energy next year. You're all computer science, kind of? Yeah. Now, sometimes students do green energy. I think there's, in a place like Ireland, there's lots of potential growth for wind and wave energy. Yeah, you're all computer science, isn't it? No, you're architecture, computer science next year? Computer science, and Regina next year? Huh? Maybe computer science? You're not decided yet. Okay. Next type of energy is kinetic energy. What is kinetic energy exactly? Energy associated with what? What exactly is kinetic energy here? When do you have kinetic energy? Motion, movement, yeah.
So solar energy is based on the radiant?
Yeah. The solar energy is probably just a small part of the radiant energy, just the energy light that you can see. I have heard of some solar panels that can use invisible light, like infrared. But mostly the solar panels just use the radiant energy that you can see, which is, you know, the visible light, I think. I don't know, maybe some use UV as well, I'm not sure. Okay, continue. And potential energy, in the picture the potential energy is here because it has energy. It could do some work, it could break open this rock if it hits the ground. So there's a potential energy here. To be more precise, you could say gravitational potential energy. Okay, continue. Yeah. So, the following. So if you can all listen. What I'm about to say is the most important rule in physics. Okay, every part of physics, electricity, mechanics, whatever, I don't care. The whole area of physics, this is the most important rule in physics. Most important, called the conservation of energy. And it says, energy can be neither created nor be destroyed. So you can't make or destroy energy. Instead, all you can do is transform it from one form to another. So, for example, when I drink my coffee, what's the form of the energy here? It's chemical. Okay, so I drink the coffee, and then if I push here, you know, this is kinetic. So the chemical energy here has become kinetic energy here. All energy behaves like this. It just changes from one form to another. Another example. What form of energy is this? It's electrical. What form of energy is this that you're looking at, that's coming out at you? Yeah, light. Yeah, radiant. And also, if I put my hand on it, what else? Heat. This energy plus this energy equals that energy. Exactly. Okay? So, write this down carefully. The most important rule in physics, you want to write it down very carefully. You got that? Okay, so question. I lift this up. What form of energy is this? I suppose so. Okay, what about if I just do this? I'm making it move. What energy does it have? Kinetic. Where did that energy come from? What was its previous form?
So what sound?
Oh, there's no sound for this one, but you're right. I didn't list all the energies.
Oh, okay.
I just list big ones. I mean, there's probably thousands. You know, you could think of anything and say it's a form of energy. You know, I don't know, paint energy or something, right? There's so many. There's so many. Okay, so this one has kinetic. What form was it previously? Well, came from me. So chemical. And what form was that previously? I could say it's the coffee, maybe. Okay, that's still chemical. What form was it before that?
Heat.
Mm-mm. Yeah, where? Where are we in the story? So we've gone from this to me to coffee.
Beans.
Coffee beans. Where do the coffee beans get their energy from? The sun. So that's radiant energy. Do you see what I'm saying? You can trace it back.
Radiant energy is nuclear energy.
And where did the radiant energy come from? Nuclear. Where did that come from?
Gravitational because of the...
Correct. Gravity pulled it together to make the nuclear process. Where did that come from? And so on. Yeah. Which really, you know, it should trouble you. It should trouble you because you think about it, this energy here, you either have to say it keeps going back forever, or it keeps going back to some point where at some point maybe all the energy ever was created. You know, so anyways, this is why you don't want to think too far back and just keep it more recent, because otherwise you could be really troubled by this. Yeah. Okay, so that's the conservation of energy. If an object is moving, then we said it has kinetic energy. This energy is from some work being done on the object. That is, the kinetic energy equals the work done to give it that energy. So anyways, what I'm trying to get at here is, let me draw it here for you. I'm going to write it here. I'll just draw this picture here. Okay, this is at rest, and it has a mass m. and then this is a mass m, and it's moving with a speed, we'll say, of v. So, this guy here has kinetic energy. Where did this energy come from? Must have been because somebody pushed it, made it move. So, some work was done, okay? And the work done is equal to the kinetic energy. But remember I said at the start of this lesson, it's not really equal. Like, I mean, obviously he could have more energy than just the energy he gave to make this move, but it doesn't matter. There is a formula to calculate exactly how much kinetic energy or how much energy this has. Does anyone know the formula? Yeah, it's a half mv squared. That is how you calculate how much kinetic energy this has. So you can see that if I make the mass bigger, it has more kinetic energy, or if I make it faster, it has more kinetic energy. So this is our first formula, kinetic energy formula.
How is that arrived?
I was going to do the proof, but I don't think there's time to do the proof. Okay, I'll do the proof. But I'll do it quickly.
Okay.
Right, can I go to the side?
Yeah.
Okay. So we said the work done, the kinetic energy equals the work done, and the work done is pushing this up to a speed of v, starting at rest, and it has a mass of m. We know the formula for work, don't we? It's Fd. We know a formula for F, it's ma, and in this story the d is the s, travelled. Yes? Okay. We know that u is 0, v we don't know, a we don't know, t we don't know, and s we don't know. Okay? If I use my formula, v squared equals u squared, which is 0, times 2as. Yes? So I can change this into 2m, I mean to say a half m 2as. I can just put a 2.5 in. But what is 2as? So that's the proof of it. You wanted to know the proof. It's okay?
Yeah.
Yes? Alright. So we'll go, so you don't need to write that down. That's the proof of the formula. Right, the next one is, you have something like a height h here, and you have a little mass on the top here of m, and it just about falls off and hits the ground. It obviously can do some work when it hits the ground. This has an energy called potential energy. Okay? And again, like the last one, there's a formula for it. Do we know it?
MGH.
mgh. And Zach, would you like the proof for this one?
If you can do it fast.
Of course I can. Right, so the proof again, the potential energy is equal to the work done. Who or what has done the work here to give it this energy? Huh? Well, not quite, because gravity didn't bring it up to the top of the cliff to give it this potential energy. So it must have been some kind of person must have lifted it up to its position and gave it the potential energy. Right? So once again, what's the formula for work?
Force distance.
4 times distance. Well, in this case, the distance is h. Now, interestingly, what's the force here? So if he wants to move this up with a constant speed, what does he need this to equal? mg, the weight, yeah. Yeah, so F equals W, and W equals mgh. Okay, so that's the proof of the second formula. But you don't, again, you don't need it, and that's the formula there, mgh. Alright, should we continue? Yeah. So that's just the potential energy. Oh yes, talking about potential energy. So if the potential energy is positive, we say the object has potential energy. I'll draw a nice little picture here for you. Okay. There he goes. His potential energy, as he falls, is positive. He has potential energy. The second situation is the potential energy could be 0. What might that mean?
Accurate.
Not,
H
no,
is
no, no.
He's on the ground.
He's on the ground.
Yeah, H.
That is potential energy of 0. We call that picture free. He's free. He neither has potential energy or, he could move left and right. The gravity doesn't really matter anymore because he's on the ground. He's free. So we say the object is free if the potential energy is 0. Now, most interesting is what do we mean when we say the potential energy is negative? What could that mean in our picture?
He's underground.
Yeah, and what is... Yes,
Wait, that's right.
yes.
So like a screen.
The potential energy is negative. But what word do we use to describe the situation? If this here is free, most people like to be free, so how would you describe the situation here?
It's a trap.
Trapped. So when the potential energy is, you say it's trapped in what's called a potential well, meaning if he wants to be free, you need to give him energy. Because, for example, if his energy is minus 10 joules, that means 10 joules need to be used in order to get him to be free. You know of this in chemistry. You know ionization? So you have the electron moving around. Yes? What do you call it when the electron is freed? Ionization. How do you free an electron? By giving it energy. So its energy is negative potential energy. Okay? I would like you to write these down, especially the last one is very important. I've already looked at an example. You can draw the picture if you want. No. It's trapped in a potential well, it says. Okay, you got that? Yeah? Harry, you got that? Yeah? Okay. Next. Conservation of energy implies that the initial energy of an object must equal the final energy. Now, you don't have to write this down, but as a formula, you could say the energy at the start equals the energy at the end, which is another way of saying kinetic and potential at the start should equal the total kinetic and the potential at the end. That's the same thing as conservation of energy earlier. What we'll do... Yeah, 2 examples. Okay. A 1 kilogram ball is dropped from a height of 10 meters. First question to you guys, how much potential energy does it have?
98.1.
Very good. That took longer than I would like, but okay. 98.1 joules. So it's at the top, and it has 98.1 joules of potential. You let it go, hits the ground, it has a kinetic energy. How much kinetic energy does it have? Very good, 98.1. Because all that happened was the potential energy here became the kinetic energy here. Yeah? How much potential energy does it have when it hits the ground? 0. Correct? And how much kinetic energy does it have when it hits the ground? Oh, sorry, I misread the second one. Sorry. How much kinetic energy does it have at the beginning? 0. How much potential energy does it have at the end? 0. And how much kinetic energy does it have at the end? 98.1. Okay. So it's a silly question. This is more of a real question here, and then we can finish. A 200-gram bullet is fired horizontally from a height of 10 at a speed of 100. How fast is it going when it hits the ground? Does this remind you of something you did earlier in the semester? What's this like? Projectile. So this is 10 meters. This is 100 meters per second. And it's 200 grams. And my question is, what is the V here? So you could do this using projectiles. However, it'd be much better to use conservation of energy. Tell me this. What type of energy does it have at the start here? What forms of energy? Does it have kinetic? Yes or no? It does. It's because it's going quite fast. So what's the kinetic energy? A half 0.2 100 squared. Does it have potential energy at the start?
Yes.
Yes, what's the potential energy?
19.62.
Yeah, we'll just write the formula out. M
9.81
G
times 10.
equals. Now, let's look at the end. Does it have potential energy at the end? No. Does it have kinetic energy? It does, just before impact, which is a half m v squared. So can you calculate the v?
Yes.
Of course you can. So let's see. Calculate it for me. So you're saying the kinetic energy plus the potential energy at the start should equal the kinetic energy plus the potential energy at the end. And this guy here is actually 0.
$14.00.
14.
I got
No, I believe. Yeah, go on. What you got?
100.976.
So 101. Zach.
My calculator is not.
I knew. I don't think it's the calculator. That's the problem. I knew the answer must be more than 100.
Because it has to be.
It's gaining speed as it falls. Yeah. So it had to be more than 100. So I believe 101 would seem right. Yeah? Yeah. Okay? Yeah. Right, so there's 10 minutes left. We'll finish off by doing those questions for a little bit, and then, well, not even 10 minutes, only about 5 and a bit minutes. So if you can just try the next lesson for a few minutes, please. The conservation of energy lesson.